Hi, welcome back. In this lecture I will talk about collective communication and collective computation in MPI. So what is collective communication? So all communication in MPI is within a group of processes also called communicators. Collective communication is a communication that occurs over all the processes in that group. MPI COM world defines all the processes when the parallel job starts. We saw in the previous lecture how we can create new communicator using visual topology function. But we start always with the MPI COM world. We can define other subset, for instance, with MPI dynamic processes. MPI provides a way to launch dynamically MPI processes. Right, so we can actually create sets that are bigger than the initial MPI COM world. However, dynamic process management in MPI is not very well supported in any of the implementations. So at the end of the day, what we need to do is basically to deal with the MPI COM world that is quite static number of processes. So the whole point I want to make is that collective computation and communication is that communication and computation that occurs at the same time on a group of processes. So programs using only collective communication can much easier to understand, because we basically can replace very complex communication pattern by just one call. This call is then implementing some of these more sophisticated algorithm for instance, exchange data between ghost cell. So every program does roughly the same. So basically call this collective function. There is no strange communication pattern visible, in the sense that it is just one call that is hiding all the complexity of sending messages from one process to the other one. So collective communication, you can think of collective communication as a large series of point-to-point communication using quite clever algorithm to achieve the goal. So algorithms for collective communication are rather sophisticated, right? So you need to look at the MPI implementation to check the detail of the specific algorithm that is implemented. So these are sophisticated because are devised by HPC parallel programming models experts. So, the certain collective have very good performance with certain algorithms. So many of these collective are implemented, following the state of the art, and in some case also beyond the state of the art of the parallel algorithm. Let's just look at an example of collective communication in MPI. So the example that I'm showing here is exactly the same example we saw in OpenMP to calculate pi as basically as a result of an integral, right? So this is the body of our code using basically two collective communication here, MPI broadcast and MPI reduce. So what MPI broadcast does is basically broadcasting one value or more values from a rank, right, that is called the root, to all the other processes. So in this case, we're using broadcast. We broadcast the value of n. In this case, is the number of cells we divide our domain to calculate the integral. So then we have the count, the type, and this is basically the rank that is the root. So the rank that is going to broadcast to all the other processes the value. Right. So then each MPI process will execute this part of code. We calculate the grid spacing. So the domain is from 0 to 1. We calculate. So this is a partial sum related to the process, and then we have each process is doing these loops by starting from the rank plus 1, and and basically cyclically taking part of this integral. So so we calculate the local sum, that is the partial sum local to the MPI process. So each process will have its own sum. What we need to do then is basically to take all these local copies in the MPI process and put it together. So MPI provide a function to reducing all these partial sum on a different MPI processes that is called MPI reduce. So MPI reduce is rather simple. We provide the value of the local partial sum. In this case is MPI, and then we provide what is the variable that you need to add it up. In this case is pi. And then the count, the type, which kind of operation, and the rank that is going to reduce to, right? So all these my pi will be reduced on rank 0 and added to pi. Just few notes about this program. So MPI broadcast is one-to-all communication, right? So we have one values on the root, and then is basically broadcasted to all the other processes. That's why it's one-to-all communication. In the specific example, we take the value of n, that is the number of processes, on rank 0, and then we broadcast it to all the other ones. Quite the opposite, the MPI reduce is all-to-one computation, because each process has its value of my pi, and we reduce to one process with just one value that is called pi. MPI reduce also has an operation associated, so it's not just collective communication, but it's also collective computation. So the operation is MPI sum, using that to combine the reduced data. So broadcast and reduce and all collective operation, they work for any number of processes, including one process itself. Right? It's very nice to use it because the use of collectings avoid to choose any specific communication pattern. Right? So we could provide a hint in a certain way, but typically all the complexity of having high performance collective communication is hidden by MPI. Also, we don't need to take care of which rank and process topology. It's all taken care by the collective communication. So communication and computation is coordinated among a group of processes in a communicator. Groups and communicators can be constructed by hand using the topologies routine that we have been studying in the last lecture. An important point is that from MPI 3 we also have a non-blocking version of collective operation. Just basically adding I before each of these calls, we've got the non-blocking version of the collective operation. So there will be a function, and also remember that the other function to basically check for the completion of the matches, right? So we saw MPI wait and MPI test that we always need in the non-blocking communication. There are three classes of collective operations: synchronization, data movement, and collective computation. So let's look at first synchronization. MPI provides a barrier that takes as an argument a communicator. MPI barrier blocks until all processes in the group of the communicator call it, right? So if we need a synchronization point at which we need to wait for all the processes, we put in our code MPI barrier. It's almost never required in a parallel program. So it's one of the performance error many people do is to add MPI barrier, taking account that especially MPI blocking communication is actually a synchronization point, so you don't really need to add an extra synchronization. MPI barrier is occasionally useful when measuring performance. So when measuring performance, we will have processes, all going at different speeds. Which one I measure, right? So if I want basically to wait for all the processes to be the same time and take characteristics time, we can use a barrier. In some unusual cases, can also increase the performance by reducing the network contention, and also doesn't guarantee that processes exit at the same time or even close to the same time. So the process basically entering the barrier, right? Enter the barrier, and then they just wait for all the other processes to arrive. As soon as all the processes arrive at the barrier, they get out, right? So MPI doesn't guarantee that they get out at the same time. The collective data movement is divided in three broad classes. The first one to all. This is a broadcast and scatter, and all to one, like gather, right? So I'm not including reduce because reduce also had computation, and all to all, right? So everybody to everybody is communicated. And all to an example of all to all is all gather and all to all. So you notice that on these slides we also have a personalized between scatter and all to all. What does it mean? Personalized means that each process gets a different data. So let's look at the first collective operation. The first one is a broadcast. We have one value on the root. In this case, the root is P0, and then we want to broadcast to all the other processes. So each process will call this broadcast. We tell which process has the value to be broadcasted. So in this case, it's going to be P0, and then after the completion of the broadcast, each of the processes will have a copy of A. So then we have the scatter operation, that you can think of the scatter operation like distributing the values on an array on one processes to all the other processes. So it's still one to all communication patterns, right? So we have an array on the root A, B, C, D, and then using backscatter we basically scatter the array among different processes. So the A will still remain on process 0, but B will be in process 1, C in process 2, and so forth and so on. The opposite operation is called gather, and you can think as a gather as a collection, right? So in this case we go from all to 1. We have a vector that has been scattered, right, across different processes. So A is on P0, B on P1, and so forth and so on. And then we collected through on P0 with operation called gather, right. So of course here we can tell which one is the root. So not necessarily should be the process 0, but we can collect here or there. Right. So broadcast is one to all, scatter is one to all, and gather is all to one. Few comments about the broadcast. All collective operation must be called by all the processes. So we are not going to have selections like, what is my rank? If I'm rank 0, I'm called broadcast. Otherwise, I don't do anything. No, all the processes need to call MPI broadcast. MPI broadcast is called by both the sender, called the root process, and the processes that are to receive the broadcast. Right. So how can basically here's an argument we provide who is actually the sender by providing an integer with the rank of the process that is sending. So root argument is the rank of the sender. So this tells MPI which process originated the broadcast and which one also receive. More collective data movement operations, and when we have all gather is very similar to gather, in the sense that the first operation is actually a gather. So we gather from all these processes. We gather on, for instance, on the on root 0. We collect all the values of the array from different processes, and then we basically broadcast from these processes to the other one, right? So all gather can be also thought as just one gather, right? So we gather on P0, A, B, C, D, and then we broadcast from A, B, C, D from rank 0 to all the other one, right? Another important communication pattern is the all-to-all pattern. That is basically a transposition of a matrix, right? So if we have a matrix, so in this case we have A0, A1, A2, and A3, we basically communicate to all the other processes, right? So we scatter. So think about all-to-all as a transpose operation with just one call. A few notes about on the last two functions. Well, MPI together, as I said, is equivalent to MPI gather first, followed by a broadcast. But of course, the MPI implementation of gather are much more sophisticated than that, so they don't implement as gather plus broadcast, right? But they have very specific algorithm to implement it. The MPI all-to-all perform a transpose of the data. Is also called a personalized exchange. It's very tricky to implement efficiently, so there are quite a few papers on how to do that. And in general, one interesting stuff. It doesn't require big of P, where P is the number of processes involved in communication, especially when only small data is sent to each process. Each collective operation has other variants. So we have the V variants. So you might find all these operations with a V after the name of the function. So why we need that? Well, so the basic routines send the same amount of data from each process, right? So in this case, if we have MPI scatter, and when we give the vector, and when this is the count, so each process will have exactly the same count, right? So this will so the scatter, we will basically scatter one value to each process. So what happens if I want to send a different number of items to each process? Well, we can use the variance, the V variance. It's called use MPI scatter V. So there is a V at the end. The V stands for vector, and these V routines allow the programmer to specify a different number of elements for each destination, one for to all routines or source. Efficient algorithms exist for this case, those as not as fast as the simplest, without the V. There are also W variants. So for instance, in the case of all-to-all, we have a MPI all-to-all W. There are two vectors routine to allow more general specification of MPI data type for each source. Recall that only the type signature needs to be matched. This allows a different layout in memory for each data being sent. So this is something we touch a little bit on MPI data type, right? But these W variants allowed much better handling of MPI data type when using all-to-all. So we also have a collective computation. We saw MPI reduce. It combines communication with computation in reduce. It can be all to one with an operation to combine. So for instance, scan and xscan. We have all prior ranks to all with the combination. So we also have reduce scatter. And we have all to all communication with the combination. And also we have combination operation either with a predefined operation or user-defined operations. A little bit about collective computation. So we saw reduce. So we have some local copies, and when we want to reduce this value to one of the process, so we can use reduce. We have a scan. So basically we have our vector distributed among processes. With a scan we keep A, and then we basically keeping adding more element to each process. We also have all reduce, that is basically a reduce plus a broadcast, right? So we do first a reduction operation, right? So we get on the root A plus B plus C plus D, and then we basically broadcast it to all the other processes. So we also have a scan that is similar to scan, but not exactly the same. In this case, basically, the A, instead of being on processes 1, is in 1, and then we keep it summing and putting the other processes. So it's like shifted. So MPI has some built-in collective compilation operation. We have been using MPI sum, but we can do other collective operation, including max, min, and some logical function, and our friend here, max lock. So this was the last slides for this lecture. In the next lecture, I will continue talking about collective MPI communication. Talk to you soon.